I would like to thank the BIM Coordinators Summit for inviting me to present and share my work over the past years. So a little bit of me, I have a background in architecture at the Polytechnic University of Turin, as well as some other additional studies and a recent Erasmus Mundus Masters in BIM. I am currently a PhD candidate at KTH, Royal Institute of Technology in Sweden. And over the past couple of years, I have been working as digital design and sustainability lead at Arco Architecture Company, where I was working to explore, develop, and integrate sustainable design methods, workflows, and customized methods in the design practice and in projects. I'm also a licensed architect in Italy and a WELL-AP, that is a green building rating system. So to give you a brief overview of the presentation, I will try to explain briefly the shift from sustainability to regeneration, how sustainability can be integrated in digital design processes, how does BIM and information management support sustainability goals, improving performance and architectural design, and the new framework of level of information need for design and analysis, why computational design is important for customized workflows and achieving design goals, and do that through showing some data-driven design use cases. So in this diagram that has been shown for the first time in 2007 in a paper from Bill Reed, and this is an updated and current version of the diagram that I'm trying to present why conventional practice and green building and sustainability is not enough, where green building is mainly focused on reducing environmental impacts and increasing efficiency, and sustainability is mainly aiming at net zero carbon, net carbon, and aiming for neutrality, not doing anything more. But we need not just to reduce our impacts, but to regenerate and create a positive impact for people and for the planet. So the first step is restorative, reconnecting with nature, having a sense of belonging. And when we think of trying to limit climate change to 1.5 degrees as the targets of the Paris Agreement or nature-based solutions, these are the first steps towards regeneration. And regeneration actually means sustaining life itself, so humans and the planet. And we need to apply living systems and whole systems thinking. And when we think of achieving the circular economy also for the built environment, resilient cities, and the new European Bauhaus can be an opportunity for that. And it requires also technology, digital transformation, but also a cultural shift to how we can do things that are actually good and positive and not make trade-offs like in the past. So regenerative design requires a holistic approach with climate, people, and nature in mind. And we have some previous approaches to it, like designing with climate or designing with nature from Olgai and Mekharg. And it requires making carbon positive buildings that sequester carbon, but not only through biogenic carbon, but also through enabling the circular economy, which is a hot topic right now, creating positive energy buildings that produce more, reverse the causes of climate change, allowing for human and natural systems to evolve together over time, and the circularity for all the resources. Traditionally, when we start a project, or if we follow bioclimatic design, we would first make climate analysis, which is a time-consuming process to understand the climate. And we try to use this in the design through sketching or through tacit knowledge that comes from experience that is hard to codify and write. And we as designers and engineers rely on it, as well as using standards and using sun charts, wind roses, or psychrometric charts as design strategies. At the same time, we've used scale models or laboratory experiments to understand the project, to communicate it with clients and other stakeholders, and also to improve the design. What has been changing over the past years and currently is that from traditional processes, even when we have CAD and BIM, we would have several design cycles, and we would verify and validate that design is compliant to regulations, to standards, and we can actually build it. When we try to apply an information management process through BIM, We can use open standards like IFC, BCF, IDM, MVDs, and also integrations, plugins, direct links through software tools that allow almost a direct integration of the design process through the simulations, and actually use this feedback iteratively in the design, and reduce the time that we actually need to do the physical models and testing and simulation correlation. So it becomes much more efficient and much more data-driven. Interoperability is an important part of our work, and it's not going away anytime soon, even though we have a lot of platforms and plugins that do this work for us from a lot of new software currently right now. But still knowing about interoperability, because standards change and because either written standards or even information management and tools, they change continuously and people get specialized, it will always be incomplete. So we need to know how do we represent buildings for architecture, for engineering, or for a certain use case. And we need to use these open standards leverage to our advantage. And this is a very easy example to demonstrate what I'm saying through information exchange through an IFC, using Revit to read the IFC and export it to a machine-readable format for Rhino, and then from Rhino making the cleanup of the model and using it, for example, in a free software like the Velax Daylight Visualizer. Whoever works with daylight design knows that the BIM models have solids for the glazing surfaces, and that would result in 4 or 6 surfaces if we have a double or triple glazing. But when we do daylight simulations, we only need a single surface for it. So we will need to clean up the model. There are some tools that can do that automatically for us, but knowing how buildings should be represented for each use case is very important, and using interoperability and open standards. We've had for a long time, over the past decade, LODs. So in the USA, they used to be called level of development. In the UK, level of definition. And they would define the geometrical and information needs of building and describe it through levels. For example, in the UK, from 1 to 7. But that is an approach that has also been shown that is too generic for the purpose of any BIM use cases. And in Europe, from almost 2 years now, we have a new standard called level of information need. And it's not a predefined way of representing, but is a framework to define the quality, quantity, and granularity of information requirements. And I wanted to highlight this because this aligns much more better with building science, building physics, and how performance simulations, methods, and tools interact and have their requirements. So we could use this a way that is not standardized, but is specific to the use cases. For example, in the case of daylight, we need for the context simplified buildings and context and the trees. We need a more detailed model of the spaces to be analyzed, and then select what are the metrics, the sky model, the material properties, or other standard that we are seeking compliance. And if we read the document, it would take 50 pages or more, and it would take a very specialist knowledge. But if we turn this into information requirements in a BIM execution plan or in a one-pager document, we can democratize the process and have not only experts carry out the evaluations or use daylight or energy or life cycle assessment, but even every architect or engineer in the office with this framework could be able to carry out evaluations that before only experts could do. So I'll go on with showing some case studies. So for example, we can perform sunlight hours with computational tools, like I'm showing in this case with Ladybug. And usually is the intuition and the choice of the designer how to use these findings from the analysis to change the building distances or see how much a square can receive sunlight. And it's not very much based on thresholds, but more on design intuition. And in this case, I'm showing using the same methods like sunlight provision, but using the European Daylight Standard, applying the rule sets of the standard, which are meant to be carried out by paper, and turning that into a machine-readable and digital method. So from a sunlight analysis on the left to a categorized image for the minimum level of performance to the whole 3 levels of performance on a building massing. And we can also extract the percentage of space in of this performance, either as a percentage or either as a surface area, and we can track how the design improves through the changes and compare it. And this is in a paper that I'm presenting at the IBIPSA BuildSim conference this year, and part of other things in the paper. So I'd like to go on to show sunlight. Then from sunlight we have daylight, which is a different, and usually when we refer to daylight, we are talking about illuminance levels in the interior of a building. And data visualization is an important part of it. Sometimes we would prefer to categorize the results, like in the 3 images above, of the useful daylight illuminance. And it would help us kind of define the different areas every 10% steps. That we have daylight, and also on the bottom image of the left there is a daylight autonomy represented in full scale color range, but showing also the 50% contour, which is usually a good threshold for a daily space. And this is to say also that a lot of preferences, designers have, architects or engineers have different preferences. Some would like to see categorized results, some would like to see a full scale color map. And for example, if we are talking to clients, we would maybe want to simplify and not show metrics, but only the qualitative parts of these evaluations. Only say which is the daylit area, which is the partially daylit area, and or the non-daylit area, which is maybe not important to have 100% daylit because it's related to the cores of the building, and so on. So moving not just a checklist of a green building certification, but actually explaining to the client why a data-driven approach and why all these things matter in the design and how they can improve productivity and well-being of people over time. As well as glare usually has been time-consuming, but with several open source or commercial tools, we can now make glare analysis with new methods much more faster and on an annual basis. And we can even think of using that at a higher level for designing the layout of buildings, spaces, and furniture. As well as building energy modeling, there are a lot of experts that do BAMs, but and also a lot of specialized tools that can have a lot of detailed settings for modeling buildings and working with a lot of files. But when we use a computational approach, or when we use plugins that are directly integrated in a design modeling environment, we can actually get faster feedback and without having to wait for a long time to have those results in the design, and actually test if small changes from the shadings or even distances or how we arrange the thermal zone or construction properties could affect the energy performance. And climate change and construction are very much things to think about and to try to improve, because we have a high responsibility and a high impact on the built environment, consuming 40% of energy and producing 36% of CO2 emissions. And population area and floor area are outpacing the energy efficiency improvements. Showing from these reports, even though they are a couple of years old, they are still very much relevant, and the building stock is set to double in the 40 years. And we can use life cycle assessment, for example, through the European standard 15798 to perform. And in this case, I'm showing some data visualizations and embodied carbon for a project I was working on. With one-click LCA, but there are many more other tools in Grasshopper, in Dynamo, or directly integrated in Revit that can perform life cycle assessments. And these are very important to influence the design as we are doing the work, but also to communicate with clients the value of every design choice, and also track the building from design to construction and also to operation, to understand the carbon emissions through the whole life cycle. And BIM and Information Management is critical to supporting these processes. as well as computational fluid dynamics, CFD shortly, is a methodology that is increasingly being used in the built environment nowadays in architecture and engineering practices, because how we lay out the buildings in an urban space influences a lot the wind patterns. If we have dangerous wind patterns or through calm, we don't even want the opposite, to have no wind circulation at all. And also verifying wind for certain direction is that is a prevailing direction is important, and uh, there is not a single metric that can capture everything. So looking at the prevailing wind directions, or looking at the outdoor comfort, or looking at the wind comfort metrics, there are all parts of the picture. So looking seasonally how the wind patterns or through a simulation affect the place is very important to place the buildings well in the location, and also think of how we would design, maybe make some smaller design interventions on the urban space, and how we would program spaces in the indoor and in the outdoor relating to wind comfort and microclimate analysis. In this slide, I'm showing some work for a project of new development, combining wind speed from computational fluid dynamics simulations with sunlight temperature and humidity tools, all computed spatially through open source tools through Ladybug. And on the left side of the image is represented the UTCI through a heat map. The UTCI is the Universal Thermal Climate Index, which is the most widely accepted index of fields like temperature, so to say. So the temperature that is actually felt from the combination of all these factors. And we can turn that into a more actionable insight when we categorize the results, for example, of UTCI through the different comfort levels. So, for example, in the UTCI model, from 9 degrees to 27 degrees is considered comfortable. And as we go slightly up through these ranges, we have a slight feeling of heat, or a more higher feeling of heat. And if we go below, we have start feeling cold. And these are all categorized and expressed qualitatively in the UTCI model. But as well as we can turn these simulations, if we think of the percentage of occupied hours of the time that these are comfortable over a week over seasons, this can become even a more actionable data and insight for the design process. So, for example, the area in blue, highlighted in blue, that is over 50% of the time comfortable, we can think of it that those are the best places during the summer season to locate the different activities, and the other places would need maybe some mitigation strategies, greenery, and so on. And it's a very complex topic because it requires looking at different levels. So looking at seasonally, looking at the percentage of time, and looking at different metrics. The City of London has made some guidelines that I'm sharing the reference, wind and for thermal comfort. And there may be also other initiatives that have done so. But it is not very well explained. They show a lot of very nice data representation of the thermal and wind microclimate, but how to get to those kind of metrics is not explained in those guides. So in this workflow, I wanted also to show a way of achieving more actionable data. So this was from my part, and I'm looking forward to the discussion and to the questions. Thank you.